Hi everyone, I want to look at today the idea of composite functions. Essentially, a composite function is where the output of one function serves as the input of another function. And we see that all the time, but it's more formally dealt with here. And as I said, full questions on composite functions haven't appeared on the Project Maths exam paper since 2012. But again, 2020 or 2021 could be the year that happens. So first of all, some talk about notation. You might see something written like this, g f of x, and you might even see a little circle symbol here. That would imply g after f of x. So in general, when applying these composite functions, you start from the inside and then move outwards. So in other words, we'd apply the f function first and then apply the g function on the output of the f function to reach a final result. So I've illustrated that by these few examples here. I've just made up this example where the f function is x squared. In other words, the input x produces an output of x squared, and a g function has an input of x with an output of 2x minus 3. Well, I'm just going to demonstrate a few different composite functions now. First of all, g after f of x. So we apply the f function first. So f of x is x squared, and now x squared serves as the input for the g function. So inputting x squared into our g function. Effectively, this says here that the g function is take your input, double it, and subtract 3. So now we have an input of x squared. I double that input, subtract 3. So my final answer for g after f of x will be 2x squared minus 3. Now let's see if it's the same for f after g of x. So f after g of x, we see that would be the f applied to the output of the g function, which is 2x minus 3. The f function is a function where you square your input. So if the input is 2x minus 3, f of 2x minus 3 will be 2x minus 3 all squared, giving us a final answer of 4x squared minus 12x plus 9. So in general, we will see that this sort of function, composite function operation, is not commutative. The order does matter. And unless these two functions are inverses of each other, and I'll be discussing inverses of functions in a future video, you will definitely see outputs that are in general not the same as the result of composite functions in different orders. You might see this notation here, what could be described as f squared of x. That's effectively just f after f of x. So this would be f of x. The output of the f function is x squared. So that would be the f of x squared. That x squared now serves as the input to an f function. So x squared all squared gives you an answer of x to the 4. You also can have composite functions in triples like this. F after g after f of x, f g f of x. So first of all, we apply f of x gives you x squared. X squared then serves as the input to the g function, which is twice your input, and subtract 3. So g of x squared is 2x squared minus 3. And then we apply the f function once again, where the f function serves as the squaring of your input. F of 2x squared minus 3 is 2x squared minus 3 all squared, giving us a final answer of 4x to the 4 minus 12x squared plus 9. So you see there that composite functions generally are not commutative. You can have effectively multiples of the same function serving in that same composite function way, and you can have 3 or 4 functions combined together for one omnibus composite function. I've done one more example here from the textbook, page 369, question 3. We're given two functions, f of x and g of x. Note this would be another way of expressing f after g of x or g after f of x. So applying the function g of x first, x plus 5 serves as my input to the f function. I square my input and add 3, and I reach a final answer for f after g of x squared plus 10x plus 28. Then applying the functions in the opposite order, g after f of x, that's g of x squared plus 3. And then my g function is simply take the input and add 5. So my final result for g after f of x is x squared plus 8. This particular question asked you to find the value of x for which f after g of x and g after f of x are equal. That doesn't mean it's equal for all inputs x. In general, they, as I said earlier, they're not the same. That is not commutative. However, there would be sometimes individual or multiple values where it is the case. So simply setting these two quantities equal to each other, we get a linear equation, get an answer of x equals -2. We were asked to verify that answer. You could do that by going through the whole procedure or simply plugging into the two different functions. So if I plug in -2 here to g after f of x, I get -2 all squared plus 8. That's 4 plus 8 is 12. If I plug -2 in here, I get -2 all squared plus 10 times -2 plus 28. That's 4 minus 20 plus 28, also equal to 12. So it is verified and it is true. So there's a short introduction to composite functions. As I said, this has not yet been asked formally in any sort of project maths exam paper since 2012, but 2020 or 2021 could be the year. Have a look at the exercises on page 369, 370 and 371, and I will have some future videos detailing some extra examples, and next up I'll be looking at inverses of functions. Thank you very much. Talk soon.